Hello everyone, this is Martin and we're with Planet Earth, and this is a kind of summary of the first two classes that we had. I want to speak a little bit about 4 points: the geoid, the P and S waves, the structure of our planet, and finally a little bit about plane boundaries. Everything that I'm speaking about here has been covered in the PPT, in the lecture. I want to reflect a little bit or answer your questions about the geoid. So thanks for those of you who were brave enough and contact me on WeChat. I didn't answer most of you, I guess. I just want to reflect on this point and answer your questions if you have any, like here in this little video. And the other points I just want to perhaps show you here, and these are those topics that would appear in the exam very often. So that's why I'd like to show you how I would like draw this. So if in the exam you've been asked to explain the structure of the planet, what am I looking for? And if I'm asking about the plate boundaries and examples, or what is, for example here, especially one of my favorites is the subduction zone. We explain with the help of a drawing what is subduction zone, then this is what I'm going to be looking for. So first of all, the geoid. Well, I'm not a mathematician and I'm not a physician, so this is also something that is interesting and relatively new for me. I'd say in general that the shape of the planet is a geoid. It's more like a potato, as we know. Now this is just a very rough idea here. Of course it's not a potato, but definitely it's not round. So if we think about what is a circle here, what like a spherical shape would be in 3 dimensions, it's not quite that. Also you can think about the geoid, so how it relates to our actual surface. So we would have usually, of course, like the sea level, like an ocean, and we would have continents with mountains. So how does this come together with the geoid? The geoid usually would be something that is roughly very close to the sea level, especially if we think about how the oceans would look like. And then there could be some difference around the continents. That's where usually we would have some kind of difference in the maybe density of the material in the planet around the continents. That's where we would find differences in gravitation, and the gravitation would be either measured by a volume and by a direction. So that's why we would say that if we have the geoid shape, the gravitation will be pointing in a certain direction, and this will not be always pointing in the same direction. That is like what we could consider the center of the Earth. It could be something different as well, but this point here will be always perpendicular, so this direction, to the geoid surface. So that means 90 degrees, and in this case then we would say that the geoid here would be taking a different shape compared to what we could say is the actual perfect ellipsoid, not even spherical, but more the elliptic ellipsoid shape. So that is how we can think about really the geoid as the direction of the force going downward, and it's always going to be perpendicular to this direction. So whenever you drop your pen in the direction it points, compared to that one, it's going to be around like 90 degrees, and of course there will be the strengths of this force that would mark out this line. But again, this is pretty much about physics and math, and they're arguing about where exactly or how we can describe this geoid shape by not only math but with the help of satellites. So you will learn much more about this when you go to the GIS class in fourth year. So for me, all that is enough is that we consider the shape of the planet as not really spherical, not really an ellipsoid, but a geoid. The next point is on P and S waves. So we've already been speaking about quite a bit about what these are, but we can also draw and why this is important, because they behave different ways. They will help us understand earthquakes. They will help us understand what the actual structure of our planet is. So P, first of all, is going to be faster wave. So that's why we speak about that first. It's going to be compressional. This bit here we're talking about P. What does it mean, compressional? It's like how a worm would be moving. So you think about a worm. How is a worm moving? It has these sections, and at certain points there will be more denser or less dense points of the section structure. So that's where this kind of density will loosen up later on. Over here we see that there's less density in this structure, in this material, than it is right over here. And this is exactly how we can think about this compression and loosening. With its compression, we set the speed, so it's fast. You can remember the actual numbers and values, but it's not necessary. At this point, I just say that this is going to be something of relevance to us, only to say it's faster. And we also know that it will be able to cross not only solid but liquid and gas materials. So crosses liquid. Okay, that's the main difference between this one and the S. Whereas the S is going to be this kind of undulating movement, or up and down. I just put it here very simply, shear or undulating. Movement, which would be something like up and down. Movement. And it's going to be slower. Somewhat slower than the P wave. And also we'll know that it does not cross the liquids. Okay, so what do we know then? That there will be layers, the structure of our planet, that will be marked out with the help of shock waves, and the S and the P waves will be behaving in a different way. So we will have these kind of shadow zones, and that will help us see where, for example, the outer core or the asthenosphere is located, how deep, how thick that layer is. And one more, perhaps even more practical use of P and S waves is that we will see, with the help of these different speeds movement, where exactly the epicenter and probably the focus point of the earthquake is. So where did the earthquake come from? These different waves help us know that. When we are speaking about the structure of the Earth, we can just go for circles here and draw like as if our planet was kind of a spherical structure or spherical shape, and we don't bother about the geoid. Anyhow, what I want to say here is that there are different layers that are made of different materials. They have different temperatures, and also we'll know that they have different kinds of like consistency, or they behave differently. Now in the center was what we call the core, but even then the inner core is what we find in the inside. There will be an outer core covering the inner core. I just put here that the inner core probably is solid. I just put an S over here, and the outer core is going to be what we consider something as liquid. I just put here an L, liquid. What we will see then is that above these are what we consider the mantle. The mantle has two layers once again, so there will be mainly a solid layer, so that is the thicker part, but the outside of the mantle would be what we consider the asthenosphere, which is again liquid. It acts like a fluid, and on this layer then we would have what we all together, so with the top layer as well of the asthenosphere, it's very thin compared to what we have here. I'll just cover my geoid here, so that would be the kind of thin layer here together with the top of the asthenosphere that we would call the lithosphere. Which again is going to be solid, and then we would have on the very top of this one the crust, which will be different from, or depending on whether we are in an oceanic or a continental plate. So that's the crust. Then partly we would say that the lithosphere is made up of the very top layer of the asthenosphere and the crust as well. Under that we have mainly what we call the mantle, and the outer and the inner core, if we just move inwards now. So it's solid, liquid, and solid. That's how we can imagine this structured layer. And we would have different surfaces here, so the Moho or Mohorovičić, and for example here the Gutenberg discontinuity, so between the mantle and the core. But we don't need to know these details for my class here right now. This is enough to know at this moment. For plate tectonics and plate boundaries, we can right away say that there are three different plate boundaries: divergent, there will be somewhere between, transform, and finally convergent. Convergent plate boundary. If I just want to very briefly answer what these are or how they do look like, divergent is when plates move away from each other. So whenever we have this kind of what we said upwelling of, well, material, we might say magma from down under, we have two pieces of the crust moving away from each other, and perhaps here we have like volcanic activity as new material builds into the older crust. So that is one reason, for example, how the Atlantic Ocean is opening up, how Iceland was formed, or how Africa is being cut in two today. So this is how we can imagine the development of new oceans, or new ocean bed, ocean floor, ocean crust, by splitting up of existing continents. So that is definitely divergent plate boundary. And so these were some of the examples: Iceland, Mid-Atlantic Ridge, or the FR triangle, so the East African ridge. These are all divergent. We could have transform. We don't have so many explicit and good examples, so this is just a surface how we can look at like different plates moving away from each other but sideways. So that's the transform. That's why I just put here arrows in the opposite direction but next to each other. So this is how we can imagine the transform plate boundary. And we have one good example here around the planet, which is the San Andreas fault in California in the United States. This is what we can bring as the example that we learned from this class. And finally, if we want to think of the convergent plate boundary, that will be perhaps the most complicated, where depending on whether we're on oceanic or continental or mixture of these two types of crust, there will be different results. So this means here really that two pieces of materials move against each other in the same direction. And here I just highlight one point. Obviously we could think about the Himalayas, where two like continental pieces of crust move against each other, but what is the most important here is to think about subduction zone. So subduction is the process when the oceanic crust moves under the continental. Under the continental crust. Yeah, so this is subduction, and this is a subduction zone when this happens, or where this happens. The reason for this is obviously there are drivers of this kind of force, this movement, why this whole crust would move, why the continental material would be moving against the oceanic. We have this two directions movement, and what we find here is that the oceanic crust is thinner and heavier. We might say denser material compared to the continental, which is thicker but lighter. Just put lighter. The material usually of this continental crust is like granite, which compared to the material of the basalt and gabbro material of the oceanic crust is going to be lighter. So that's really the difference here, the material and the thickness. And what will happen in this case is that if we have this kind of thin but dense material, it goes deep down under. Here it can be around a couple of kilometers, maybe 10-20 kilometers deep. At that point, this material, thanks to the heat of the earth, will melt. The magma that is formed from this melted material can come to the surface, and then we have volcanic activity. You don't necessarily need to have continental crust. Two pieces of oceanic material can also hit each other, forming this subduction zone, and in this case we would have things developing like the islands of Japan, so the Fuji, volcanic activity around Fuji, or also if we think about New Zealand, some of these islands, and also the whole Andes. So South American mountains are all result of this kind of subduction zone or convergent plate boundary activity. So this is then what we definitely need to remember: subduction zone. What happens here? The material melts. What happens with that melt material? Comes to the surface and forms volcanoes. Reason is the difference in the material density and thickness of the main composing rocks of oceanic and continental crusts. So these were then just some of the points which I just wanted to cover real quick. And if you have any more questions, then you can always try to contact me on WeChat and I'll get back to you. No other way than here in the form of a comment answer in a video.